Well, good morning. The very first topic we're going to take a look at will be perpendicular bisectors. So what is a perpendicular bisector? It's defined as a line, segment, or ray that passes through the midpoint of a segment and is perpendicular. So definitions in math are very boring, but they're very straightforward. What you're looking at down here, segment AB has been perpendicularly bisected by the line that passes through C and D. What tells us that it's been bisected is each segment is congruent, and we have a right angle here, so it meets at a right angle, and that makes it perpendicular. Nothing to it. So we say if CD is a perpendicular bisector, then AC also equals BC. That's the second part of this. So any point that lies on this line, it doesn't really matter where it is. It could be here, it could be here, it could be below. If you lie on the perpendicular bisector, the key word here is equidistant. You're equidistant from the endpoints. So any of these points on this line are going to be the same distance from A and from B. Later on we'll talk about what an isosceles triangle is, but essentially any of these points, if you connect them to A and B, would create an isosceles triangle. So what do we need to know? Well, we need to know that part, and the other part is, if you know that something is equidistant from 2 points, we also can say that it lies on the perpendicular bisector. That was important in our constructions activity. So what are we going to be asked to do about this theorem? Well, for example, if you're given this diagram, the line that goes through points S and R is perpendicularly bisecting the segment from Q to T. So notice that these two pieces are congruent. Well, the other part of that is that any point that lies on the bisector should be equidistant from Q and from T. Or in other words, these two segments must be the same. So it says solve for the segment RT. Well, the way we can figure that out is by first finding x. So we can tell ourselves that, well, 2x plus 3 is going to have to equal 4x minus 7. So if we were going to solve this, we'd probably just get rid of 2x from both sides. And we get, okay, 3 is equal to 2x minus 7. So add 7 over, we're almost done here. 10 is equal to 2x, and if you divide by 2, I'm kind of running out of room, but, oh, you know what, here we go. It looks like 5 is going to be equal to x. Or in other words, x is 5. Well, maybe I don't want to actually circle that because I didn't answer the question. What are they actually asking us? Oh, for RT. So we got to go back. Say, okay, well, RT is 4x minus 7. And if x is 5, we can just plug that in. So we get 20 minus 7, or 13, for an answer. Now we've answered the question. RT is 13. And remember, good thing to know, well, for now and forever, is whenever you're given an equation, you can always go back and plug it in and make sure everything works out. So it looks like we got that RT was 13. If you tried the other segment, which should be the same, 2x plus 3, plugging in 5 would give you 10 plus 3, or 13 as well. So what's also important is that those segments actually are the same. Otherwise, something went wrong in the problem. And always make sure we actually answer the question. A lot of problems that make you solve for a variable ask you actually to find a length and plug it back in. So anyway, there's one way we'd be asked how to use a perpendicular bisector. We can also use the converse of that theorem. And that's this right here. Oh, ignore that. That was from the book, sorry. Well, it wants us to know what WY is. Well, if you look at from X to W and from X to Z, we have the same length here. Or in other words, x is equidistant from W and from Z, so by our theorem, that puts x on the perpendicular bisector. Well, that's important because that means that WZ has been bisected as well. And if from Y to Z the length is 3, from W to Y the length needs to be the same. So WY would be 3 there. All right, easy money. So what else? Well, turns out that the constructions you make on a triangle, and there are going to be 4 of them we'll get to, they create something called concurrent lines. What that means is when you have 3 or more lines that intersect at the same point, that's what we call them, concurrent. And the point specifically where they meet is called the point of concurrency. One of those such points is created by the perpendicular bisectors. They meet at a point that's known as the circumcenter of the triangle. It turns out that the circumcenter is equidistant from every vertex on the triangle. In other words, the points of the triangle. So how do you use that? Well, here we go. It says, find SV if S is the circumcenter of triangle QPR. It says QR is 7.79, PS is 4.25, and if necessary, round your answer to the nearest tenth. So here we go. So S being the circumcenter means that all of these segments have been bisected, but it also means that it's the same distance from S to every vertex. So all of those pieces are the same as well. So if SP is 4.25, that means SR and SQ also are. So we're going to have to get creative for a second here if we're trying to find SV. But what we're really going to do is just focus on this triangle. It's not any triangle, it's a right triangle. So we know that a little theorem from long ago, a squared plus b squared equals c squared, the Pythagorean theorem. We're going to end up using that one right now. So if we just focus on the triangle, sorry about that, we can focus on the triangle from S to V to R. Well, we know that the hypotenuse from S to R is 4.25. We can figure out the length from V to R as well. Well, the whole thing's 7.79 from Q to R, but since V is the midpoint, we can divide that by 2. Just take out your calculator here. So 7.79 divided by 2, 3.895. And I'm going to just leave that whole decimal there. I'm not going to start rounding to the nearest tenth until I get to the end. And later on, we'll show you how to store all this stuff in your calculator so you can do exactly what I'm saying. So now if we're looking for SV, we know that a squared plus b squared equals c squared, or I'll just call it SV squared plus 3.895 squared. That should equal 4.25 to the second power. Whenever you use the Pythagorean theorem, it seems like you're always adding, but that's only if you're looking for the hypotenuse. You really end up subtracting in this equation if you're looking for one of the legs, and that's what SV is. So I can multiply these guys out right now, or I can do it all at the end, or that's what I'm going to do. So we could say SV squared is going to equal 4.25 to the second minus 3.895 squared. And we'll do that whole calculator problem at the end. So let's go ahead and punch that in. 4.25 to the second power minus 3.895 to the second. So you're going to get a repeat long decimal there, 2.891475. It's all in there. What I'm going to do from there is actually take the square root. So how do I want to write that? Oh, you know what? I'm just going to write it all out for today. So 2.891475. And then we'll take the square root of both sides. And at the end, SV is going to be, you have a repeating decimal there, or not a repeating, but a decimal that carries on. And if you round to the nearest tenth, it's going to be 1.7. So that one's pretty difficult. I think we'll have one like that on the from the examples in the back of the text. So when you're working with perpendicular bisectors and you're working with the circumcenter, you end up having to use the Pythagorean theorem to solve for that side. So that was pretty involved, but not much to it. I think you can handle it. All right, so we're going to take a look at a couple of practice problems here. We actually have a video from Mr. Clement that will go over a couple of these. So we're going to focus on 1 to 14, but he's going to work out numbers 1 and 6. And those were kind of like the first examples. And then I believe he's going to do number 7 here. And we'll display the problems on the projector in just a second. So number 7 will be like the last one I did. That'll probably be the toughest one for you. And then 11 and 13 as well. So we'll give you a second here to go ahead and get started and try some of those out. If we have time, we'll show you a couple answers, but if not, we can you can go to our eCadence page and see some solutions. All right, let's get to it.